Okay, hello. So next day with some category theory. So what did we do yesterday? So we spoke a little bit about categories. We gave some examples. So a category is a bunch of arrows with a nice operation that is composition. And we started to speak about functors, which are like maps between categories. And I think I left a small exercise, like to figure out what is a functor between two categories with just a single object. And anybody came up with a solution? Not really. So any ideas? What can it be? And it's something I think you already know what it is. So a functor should map the object to object. So on the object level, the functor is quite obvious what it has to do. It's only the question what it might do to the arrows and what are the laws it will. Yes? No. So applicative is a certain kind of a functor, but here we will consider any functor, not what are applicatives in this setting. That would be also maybe an interesting question to ask. But here we're asking about any functor and what this map on the arrow level will do to these arrows from this object to itself. So what are the laws it has to obey? This map. First, we have the identity arrow. So what does it have to do with the identity arrow? Yeah. So it has to preserve the identity. And the second law that it has to obey? Sorry? Not really. It's more, but it's about the composition, that it has to preserve the composition. Yes, because these are what functors are about. They preserve composition and they preserve identity arrows. And here, every arrow is composable, and we know that this category structure here is actually the same as saying that M is a monoid. So the functor, and because the composition is the monoid multiplication here, preserving the composition means actually preserving the monoid composition. So the map should preserve monoid composition. So it preserves the unit and it preserves composition, the monoid composition. So it is a homomorphism of monoids. So it's a very natural thing for monoids. Yeah. So this way you can see kind of functors are more general things than homomorphisms of monoids. In the same way as general categories are more general than monoids, they can have more objects, so more arrows. Okay, maybe we should relate this idea of a functor to what you know from Haskell. So in Haskell we have a class functor f, where where we have a single method, fmap, and what's its signature? A to B, fa to fb. So does anybody see the connection between this definition of a functor and the definition of a functor I gave you? So so in the categorical setting, we had this object map that maps objects to objects, and this part is hidden here. That this higher kind of type f, its kind is star to star, so it maps types to types. So it behaves like a object map for the Hash category, where objects are types, and they will be mapped to types. So great, we have this part, and then functors also maps arrows to arrows, and this is this part, that it takes an arrow and map it to an arrow from f of a to f of b, and this is the same as I defined. Is it here? As I wrote here, that we have a map from arrows from A to B to arrows from FA to F of B. So this is fmap. Yes. So the as you can see, the functor in Haskell, there are these two things. One is the higher kind of type that behaves like a map of types from types to types, and the other part is the crucial fmap. And then you have the laws that are written in the comments of the Haskell class, that it should be associative, it should preserve the composition, and it should preserve the unit.
So is A to B the category?
Sorry?
Is A to B the category?
You mean the type of arrows from A to B?
Is that the category?
What is the B? If B would be a category itself, then you could make a category structure for every A. But I'm not sure if that answers your question.
I'm just trying to understand. You have like A to B, and that is being transformed to FA to FB, right?
So this is the part how you map the arrows from the Haskell category, where types are the objects, and things of type A to B are the arrows.
Okay. Yeah. Thank you.
And in Haskell we actually only consider endofunctors, because this class, I think it assumes that you take something from kind star to kind star, but maybe I'm not right. Maybe you take kind star to arbitrary kind. But if you restrict yourself to this kind of functors, there will be only endofunctors.
What's an example of a functor which is not an endofunctor?
For two different monoids. So most of functors are actually not endofunctors. Okay, and then so some example that you know, for example, there's maybe, which is an end of functor from husk to husk. And if you take a type A, it maps it to maybe of A. And if you have a map from A to B, you'll get a map from maybe of A to maybe of B, which maps nothing to nothing and just of A to just of f of B, if this is f. A list functor would be another thing that contains a list of things, and you can map over the elements with a given function. And the next thing that is quite important when one starts to study category theory is that functors actually have additional level of structure that is available. Because if we have a functor if we have two categories C and D, and let's say that we have two functors f and g that takes an object A to f of A and g of A, it's quite natural to actually ask that there might be some natural ways of transforming one functor to another one. And because we are in a categorical setting, we actually could ask for arrows from this f of A to g of A. Let's maybe use a color. Let's call it n eta of A. And this turns out to be a very useful thing requiring some conditions. So the subject here is natural transformations of functors. And the good question is how to actually define this naturality condition. What can we ask for a functor transformation to be to obey? Like what kind of rules you would like to have? Because if we have only such mappings, it wouldn't be probably enough in many situations. So what we actually have for a functor is that if we have A to A prime, a map, we have this F map F and F map here. So we could draw a diagram like that, and a transformation is a natural transformation if this diagram is commutative. So it doesn't matter if you F map first and then map, or go the other way around. And this is a very natural way of actually defining arrows between functors. So let's use a double arrow. And actually, if you take any two categories C and D, and you consider objects as functors and morphisms as these natural transformations, will you get a category out of it or not? Probably yes. It shouldn't be very difficult to check, because we only have to check identities and compositions. So do we have identity natural transformation? So F and G are the same functor F. So what should we pick as eta of A for an identity transformation? So we have F of A and F of A. Exactly. We don't have choice. We have to take identity of F of A. Will it be a natural transformation? So will this diagram commute? So we have F map identity and identity F map. This is the law of identity, that they are equal. So great. We have a good candidate for identity. Now we have to have a good candidate for composition. So if we have another functor FGK and another transformation epsilon of A, how can we define a composition? What should we write here? What do we have to check? We have to check if it's a natural transformation. So we have to check if some diagram commutes. What kind of diagram? So we know that this diagram commute, and we know that this diagram commute. And we want to check that this outer one commutes. Does it? So we want to check that here and here is the same as here and here. But here and here is the same as here and here, which is the same as here, which is the same as here, which is the same as here. Okay, so it's a natural transformation, like really easily. So we have a composition, we have identity. The composition is associative because what we do here is we are composing arrows in inside a category where the composition is associative. Will the identity be identity? Yes, because it's an identity in the underlying category. So if these epsilons are identities, this transformation is eta composed with identity. So it's itself. So yeah, we have composition, we have identity, and everything looks all right. So we have a category for every two categories. Functors between them are category by itself. So how actually natural transformations are reflected in Haskell? New type, let's call it nat. And what would you write? So first we need two things of this kind, because we need the two functors to encode it in the type. So f of this kind and g of this kind. And if we have two functors, what could be a natural transformation? So we need these maps from f of a to g of a for all a. And there is some difference between this type and what is used here in this definition of a natural transformation, and the difference is slightly hidden here. There's something that is not written in this definition, that is imposed here. Is this commutativity of these diagrams. That a natural transformation in categorical setting is something that for every a you have these arrows, but you also require that this diagram is commutative. And here this is hidden in this parametric type. And it's kind of known that this parametricity implies this condition. I haven't seen a formal proof of that, but I can imagine one. And maybe it would be interesting to see some examples, how these natural transformations look like in
because we can't do anything with the a.
Yes, but formalizing that to get a proof is more challenging. Yeah, it's the challenging part. Okay, let's try to write something of type identity to maybe, and let's call it just. So yeah, there should be a natural transformation from identity functor to maybe, which just construct the justs, and anybody knows how to write it.
I don't want to jeopardize this, but I don't think half of us have used parametric type. Can you, I don't know, is it like opening a wormhole if I ask to expand on that?
To expand, what is this for all? This, sure. So this required n-rank types, And this for all means that you don't have really access to this A, because it can be any A. And so whatever you want to put here has to work for any A you want to work with. So it cannot be, you cannot assume that A is, for example, an integer, or has some constraint like from num class or ic, or like you might want to put a show which maps something of type show A with a constraint show A to A, which might look like a natural transformation between identity functor to itself. But because of this constraint, it doesn't work for any type, so you cannot put it here. It will only accept, the compiler will only accept something that works for any A. And then if you want to work with something like that, if you have something of type for all A blah blah blah, and you want to do something with this, like you accept it as an argument, then this function that you will operate on this thing will have to deal with any A, where you don't have really access to what the A is.
So if you have a constraint, then it's not natural transformation in category class, but could it be a natural transformation in a different category where the constraint kind of doesn't matter because the category is restricted?
Yeah, sure. Okay, so so any idea how to write a natural transformation from identity to a maybe that will work for any A? Is there a function that transforms something of type identity of A to maybe of A for all A?
What are the constructors of identity?
It's identity, and it has the deconstructor, which gets the thing out of identity, and it's called run identity, I believe. So, yeah, so one thing that we need to like unwrap the identity with this. Okay, so let me try write the definition so you have everything. Identity of A run identity, and this is of type A. Run identity, I think so. And it's a functor where fmap just maps the A. It's quite trivially. And maybe, everybody knows maybe? It has two constructors, nothing and just. So what do I have to put here? Just is equal to not of
lambda A arrow just A?
No.
New identity compose just.
Yeah. So just compose with run. Yeah. So we unwrap the identity, we get the A, and then we wrap it in maybe as a just.
Yeah, you could do that with the lambda. Impact with better matching impact identity.
Yes, you can write take A. Yeah, you can.
Could you make it backwards?
Hmm?
Could you make a natural transformation from maybe to identity? No, from maybe to identity.
From maybe to identity. Can you?
No.
No, why? Please try. Yeah, what will you do with nothing?
I would pure it.
I will blow it with error. That's the wrong answer. So yeah, this is one possible natural transformation. There is another one. Yeah, with using nothing. So we could put const nothing. And both these functions are such that they don't care about this A, so it will work with this rank n type. So this is one simple example. Another example that
Are both valid? Because the second one seems kind of cheating.
yeah, but it will work. It takes something and produce nothing, which is a maybe. And it will be maybe of A for this A that it comes from.
At least it seems kind of useless.
It is kind of useless. And does it satisfy this part? Like let's try with this thing.
Yeah, it does. You always get nothing.
Yeah,
Or maybe
this works. Yeah, and the other one. If you take f map, and f is identity, so it maps A to f of A, wrap in this new type stuff, and then here what we get? We get just f of A, and the other way around. So we start with A, we end up with just A, and then use fmap for maybe, which will turn it into just of f of A. This is what we got the other way around, so great. And this is how natural transformations should work. Okay, another nice example is something of it should be this way, maybe. So let's call it hash. So yeah, if you want to forget about the left part, the error, something that you shouldn't do. But anyway. Not off. Any clues what to do with this either?
Well, we need to unwrap you want to work with the right, right?
Yeah, what we want to do with the right? Extract and map it to which part of to just. So we want something that map right A to just A, and left to nothing. So this should be either const nothing and just. Either. Yes? Is this a natural transformation? Which is asking to check this part explicitly. So the easiest way to actually imagine it is actually recall what are the definition of functors on the both sides. So what is a functor for either? What it does to either? It maps over which part? The right part. And what does the functor for maybe? It maps over just. So it actually maps, here will map over right, and here will map over just, which is great. And this part is preserved, left and nothing. Do you see now that this will work? If you take right and map it with f, so you get something right f of a, and then this right goes to just. And this is the part we'll use in a second here. So this right a is mapped to just, and then just is f mapped to just of f of a. And then the nothing part, the left part goes to nothing, which goes to nothing. No, left goes to nothing, and here left goes to nothing, goes to nothing.
Right, so this is working with every, I don't really have the terminology here, but with every branch that you
Yes, yes, exactly.
What happens if you start having types with hundreds of branches? I mean, this seems very naive. Is there like a more generic way to see it? That's kind of what I'm wondering about. If you are
You go to a mathematician, he wrote it down, and
yes,
you have a paper.
that's the simple solution. You like it.
Almost. Like in papers, usually people skip that part because it's trivial.
In Haskell, if any function which has this parametricity condition will obey naturally the naturality condition.
Yes, yes. So yes, because of this for all a. So you're kind of shielded against making such mistakes. But still, it's really good to know what it gives you. When you're imagining what you're doing, it's quite useful.
Is every function of type you type a functor?
You can always make something a functor. For example, you can always say instance, let's call it a functor x, where fmap of x is equal to x. No, it will not work. It will not type check. No, so no. I think there should be types that you cannot make a functor. Though it's quite hard to imagine one, at least at the moment. Maybe after a lecture we can speak about it. Okay, let's so Haskell has this return function. For every monad, it's defined in a monad class. And I would like to check if we can define something like this: identity to m. maybe let's call it return prime. So what should I write here? Yeah. And will this part work? Like to check this explicitly. So one part is the run identity, which actually this run identity is a natural transformation by itself. But just because you cannot define A like type A, you have to wrap it in some name, which is called identity. So this run identity is a function from identity of A to A. But it's actually a natural transformation between this type and the real identity functor on the category of Hask, which is this one, which is hidden here, like not written anywhere. So this part is the natural transformation. And we already know that they compose well. So if you have two natural transformations, the composition is a natural transformation. We only have to check if this return is a natural transformation. And this return is a map of type monad M A to M of A. And if you take A to B, is F map F return M of A, F map M of B, and return. This is one of the laws that return has to obey. So it's actually required from the definition of a monad for this map to satisfy this condition. And maybe later, if we get to that point, you'll see how mathematicians define a monad, and that this part is part of the definition of a monad, that it is required that return is actually a natural transformation from identity functor to this monad M.
So when it says A to B on the left, it actually means identity A to identity B.
Yes. So this is just F. Mm-hmm. Because this is how identity functor works. I have some other examples that you can try to solve yourself. Like to write something of this type. Identity and here let's call it C. So this is something of right kind. These are arrows from C to something. So maps from C to some stuff. And this is a really nice functor, because if you have a map from C to A, and if you have a map from A to B, how to get a map from C to B? Oh, I already wrote it, like compose. So this gives the functor instance for this type, which is used in Haskell. And you could like try to define natural transformation from identity to this functor. Or another thing you can try is to write something of type const A to either A, where const A is this type data A, B, consts and something here of type B. Okay, I think it's a good to make a break now and have a little bit more time on the final lecture. Yeah, so if you have any questions, please ask. Otherwise, grab a coffee. Okay, so I actually can give you a choice. We can do either of two things. We can either do something that will be more Haskell oriented, which will be a little bit about something which is called Lambeck lemma and F algebras, and or we can speak a little bit more about monads in category theory. So maybe we can make a poll if you want to have something that would be maybe useful at some point in Haskell, maybe not, or something that will be probably not useful at all, but will give you another perspective on monads and how mathematicians came up with the monad. So who's for the first choice? 1, 2, 3, 4, and for the other, well, judge yourself. Who is bigger? Come on, not everybody raised their hand. Okay, so I have to count again. So for the first choice.
What was the first one? Is that the
F algebras and functors. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And for the other? 1, 2, 3, 4, 5, 6, 7, 12. I actually hope much more for the first one. Yeah, but it's
I can change my vote to the first one if you want. I'm on the fence.
No, it's immutable. Sorry, we're in a Haskell class. There is one very useful concept in category theory that comes up very often, and this is called adjoint functors, and maybe it's a very good idea to introduce adjoint functors on an example that you already know. So let's consider the category of monads and the category of sets. Not monads, monoids. So we already know that monoids have much to do with sets because they are always built on top of sets. A monoid is a set with particular algebraic structure, the multiplication and the unit. So we always can forget about about the monoid structure. So if we take a monoid M with multiplication and a unit, we can just forget about what we have. And this is a nice functor. So if you have a map of monoids, this is defined as map of underlying sets such that, and then are the properties, which is preserve the multiplication, preserve the unit, and so on. And because this is actually map of sets, of underlying sets, forgetting about the algebraic structure gives a well-defined functor. So if you have thing like this here, you will get a map from M to N, and this is well-defined functor now. On the object level, it does this. On the arrow level, it just forgets that this map obeys more rules than what it must do in set. So this is one part of what we can do with a monoid. But it turns out that also we can construct monoids out of sets. And some of you already know it. Like if you take any type A, you can actually take, if you take type A, you can take the least type A. And that this thing is actually a monoid. Because how lists work, you can concatenate list and you have an empty list. So you get an identity, and if you have two lists, you can append. And we'll mimic this construction here on the set part. The only difference is that here is an arbitrary type A, and here we'll consider a set of things, which you can think of like a set of constructors or something like that. So we want, if we have a set S, we want to construct a monoid which is as free as possible, which means it obeys only the rules it must obey and nothing more. And we want to build it on top of S. So the monoid has to have a unit. So we have to, the set must contain a unit. Like we have to take something that is a unit, whatever it is. Like you can take a symbol. But then also if we have let's say some element S1 of S and some element S2 of S, we want to have S1 times S2. So let's take all the words that looks like this, that has S1, S2 until Sn for some n less than infinity. So our monoid will contain all the words pulled out of these elements of the set S, where Si belongs to S. And the empty word will be our identity. Like we'll call it explicitly. And this is our monoid, which is a set of words built out of this dictionary. So we take this set as our M. Okay?
Does the infinity notation mean that there's a finite number of elements?
Yes, I want to take only finite finite words. And then how to multiply two words. Stack them together, as in this. So you see the correspondence here, I guess. So now, is this construction functorial? So if we have a map, will we get a map of monoids? So if we have a map from S to S prime, we'd like to map this word to something. What can we do? Yeah, we don't have much choice. We have to map it to f of S1 times f of Sn. Is this a good map in this category of monoids? So does it preserve identity? So an empty word seems to go to an empty word. And then multiplication. If you have two words, will it be preserved? Like if you stack them together, then map, then you put this component-wise, then you unstack at the given point, and you get it back. So this is a nice monoid homomorphism. I'm not sure if I define what a homomorphism is, but this is what mathematicians use for maps between some algebraic structures, like monoid homomorphisms, group homomorphism, and so on. Okay, so we actually have this F that constructs a monoid out of a set, and we have the forgetful functor. And it turns out that this is a very particular pair of functors Okay, so the interesting property that it satisfies, it's this one. If you take all the homomorphism from f of S to M, which are in the category of monoids, it turns out that this set of all the maps from f of S to M is actually isomorphic to all the homomorphisms from S to U of M in the category of set. Okay? So first, our aim will be to try to show this property, and then we'll follow. Okay, so what it means? It means that if we take S and take the free monoid span on S, then all the maps from this free monoid to M actually comes from set maps from S to the underlying monoid. And this is kind of a definition that mathematicians use for freeness, that this map from set S to underlying monoid M, some monoid M, is the same as map from the free monoid to M. And let's try to see why it holds here. So if we have a map from S to U of M, can we define a map from this? It should be called F of S. Can we define map from F of S to M? So we have some map, let's call this F. And let's try to define the map from F of S to M. Any ideas? So F of S contains these words. S1, Sn is an example. And this belongs to F of S. And we want to end up somewhere in M. Any suggestions? What can we do?
The empty word maps identity.
Yeah, okay. So the empty word identity goes to identity. And what to do with a word?
Break it down and word to its own word.
What should I write? We have this F that takes S's, like these ones, S1, Sn, and constructs something in U of M, which is the underlying set of M. Okay, so it's not some mysterious thing. It's a concrete thing. So if we take F of S1 and F of Sn, we have such things. And what we want to do with it? Multiply it in the monoid M. So a word like this goes to a computation like this. And it will map identity to identity. Will it preserve the multiplication in this free model, free monoid? So if we have S1 Sn times S1 prime Sn prime prime, then this is equal to this is in F of S. So this is this word S1 Sn S1 prime Sn prime. And this is mapped to this Fs1 times Fsn Fs1 prime Fsn prime prime. Okay, this is one part, and the other part, if we want to check if this is a monoid homomorphism, we have to check if this is the same as mapping component-wise with F. So this will go to Fs1 Fsn, this part, and this part will go to Fs1 prime Fsn prime prime, and now we multiply in M. So the only difference is brackets, how they are written here and here. and by associativity of a monoid, you'll get an equality. So, so this way we defined for every map from S to some underlying set of some monoid, a map from a free monoid to M, to a monoid M, which is a monoid homomorphism. So this is a monoid. Okay, so this is this part from right to left. The next thing to observe is that if we have two such maps, F and F prime, such that they will be equal here when we construct these maps on this level, they must actually be equal. Because what this constructed map does with S, the word that contains just a single letter from our alphabet, it maps to F of S. So if we have two such F and F prime that here on this level are equal, it will mean that they are equal on words of length 1, which means that they must be equal. So this is one to one. It doesn't glue any arrow. And the second thing is to actually see that every map on this level comes from such a map. And how to have a candidate first for this map if we are given with this with a morphism like this.
Just look what it does on the single letter words.
Exactly, because we have this S here as single letter words. And then if we do this construction for this, will we get the same map? We will, because anything that we actually use to define this map from this composition, we use only the composition on M. Maybe I should write this. So let's say that we have FSM, and then we define a map from S to U of M by saying that S goes to F of S, and this is our G. And now we define a map from F of S to M using this construction coming from G. So we take S1 Sn, word like this goes to G of S1, G of Sn. This is by definition of our construction. But G is defined in such a way that G of S1 is actually equal to F of S1 times F of Sn. And this is equal F of S1 Sn. So we get the f back. So okay, so whenever we have a map like this, it must be defined by a map like this, and we know how to do that. So this is one-to-one and onto. So this is actually a bijection. Because these are just sets, like sets of homomorphisms of some particular kind. It's actually a little bit more true about this this map, and the more that is true about it, that is actually natural in every variable that you can see. It's natural in M and natural in S. And the naturality which I'm speaking of is the one that I was speaking before. So if you have a map, we'll not prove it, so don't worry, but just to have it somewhere. If we have a map from, let's say, M to M prime, then we can map these homomorphisms from this to f of s m prime just by composing with this map. So you take a map from f of s to m and then compose with this. You'll get this. And the same you can do here. Because u is a functor, so we can f map under it. So we can get map from s to u of m prime. And here we never actually mention what is m. So we have this isomorphism here as well. And what I'm trying to sell you that this diagram commutes, that it doesn't really depend on m in a functorial way. And the same on s, but it will be contravariant. This is covariant because we post-compose, and here we will have to pre-compose. So it will be analogous, slightly different, but and sometimes checking all the conditions in category theory is quite daunting, but nevertheless possible to do. Okay, then then there are actually other characterizations of adjoint pair of functors. So here we have one example that f is left adjoint and u is the right adjoint because of the positions they take. And the definition of adjointness is exactly that you have a bijection on home sets that is natural in a way I just spoke before. And any such natural transformation can be actually characterized also by some algebraic properties of which are very handy for various manipulations, and let's try to recover a part of it. So let's consider home of monoids from f of s to f of s. We know that here we have identity of f of s. And this is isomorphic to hom in set from S to where? No? So what is M? M is Fs. So we have to write U of M, U of F of S. So this is mapped to some map, which is usually called identity of the adjoint pair, and it is a map from S to UF of S, and also if we take hom in set from U of M to U of M, and we have identity here, and this is isomorphic to hom from in monoid we have to take f of S. What is our S? F U M 2 to M. So we get another map, which is usually called counit of an adjunction, and this is mapped from FUM to M. One can actually characterize adjunctions by these maps, this eta and epsilon, and for any adjunction, this will be actually natural transformations, because we require the naturality here, and it will go down to naturality conditions of this natural transformations from F composed with U to identity functor, and from identity functor to U composed with F. And there are two so-called triangle inequalities that I will not write them down maybe, but they say something about how these maps compose. Okay, maybe we'll come back to this later if we have enough time.
Unit and co-unit return and extract. So unit and co-unit, do they correspond to the return and extract of the underlying the monads of monad?
1 second. Yeah, so it actually turns out that we'll be able to construct a monad out of this, but I need to say a word what a monad is. So monads. Monads are functors, very, very peculiar ones that you already know from Haskell. So, and these are actually endofunctors always. So if we have a functor M, which is a functor, And as you already know, in Haskell there is this, it's not in the definition of the monad class, there is, but nevertheless there is this join operation of type monad m of a to m of a. So let's give some examples. Like if we have a list as a monad, and we take list of lists of A, we can concat and get a list of A's. If we have maybe of maybe, so we can map nothing to nothing, or just of nothing to nothing, and just of just to just. So we just collapse the tree one level. Okay? And actually it turns out that giving bind and return is the same as giving join and return. This is a small exercise for the curious ones. And mathematicians define monads in this way, using join rather bind. Possibly, possibly because this is much more nicer indication what actually is happening. Okay, so we'll follow this join to define a monad. So a monad comes with this join and return, where return is a natural transformation from identity functor to M. This is return. And then with another natural transformation from M composed with M to M, which we'll call join, also a natural transformation. Where this composition is a functor composition. So you take C to C to C, and you just do it twice, and then you require to have a natural transformation. And then there are the laws, which are very similar to the laws of a monoid, actually, because there are two requirements: that the return is actually a kind of identity, and that this join is associative. So associativity of this join would mean something like that. If we take M composed with M composed with M, so this is a functor from C to C. And we can do either join M, which takes M to M composed with M. Maybe I'll do this. I will write join A. Okay, so component-wise, and if we take here join of f of join on the component m of a. So if this a is m of a, we'll get a map from m composed with m of a to m of a. Okay, so this is this map, and then we can join a to get m of a, or we can take this map and use f map of it. So let's write it as a Haskell. F map of join m of a. Or in mathematical notation, this would be m of join a. And this will map to m of a. And we have a join here. And this equality is written in comments for the monad class in Haskell. Maybe it's phrased using bind instead of join, and probably that's because it's less visible what it really means. But it boils down to this kind of associativity condition. And then if you take the join and we want to have some kind of relation between identity, so identity, which m of a. If we take return m of a on a component m of a, this will be mapped from m of a to m of a, and then we join. This should be identity. So this is equality. And the other one, if we take m of a and we take f map of return, then we get a map from m of a to m of a, and this should be equality. And if you forget about this dots here, this functor composition, but take like a product here, and if you'd forget about the a's, here you would get something that looks like associativity for monoids. Like you take a triple element, then you multiply the first two, and then multiply the results. Or put the brackets the other way around. First multiply these ones, and then multiply the results. And here, if you take an element of your monoid and map it to the first one, so take the identity on the first component and then multiply, which is identity times m, or the other way around, take m times identity. In both cases, you should get the m. So they look very, very monoid alike. Okay, so these are the equalities, and for any adjunction, like we had here, monoid fs m home set as U of M, we actually can define a monad here. And let's take a functor M from set to set, which is the composition of S and U. So we can first take F that goes to monoids, and then we can forget that we had a monoid. Okay? And it turns out that this M is a monad. And for that we need to define two maps. We need this identity, so we need a natural transformation from A to M, which is equal U composed with F. Let's check if we have something like that. Okay, so we have this map. Does it agree? Okay. So we want a natural transformation from identity to should be M of A. Do we have one? So what we have we already found out that if we have this adjoint pair, we have this natural transformation eta that is a natural transformation from identity to UF. So this is what we need here. I need help with the mic. Once again. I need a volunteer. So you're holding. Yeah. So we have this natural transformation that we actually need, here. This eta. We got it for free. And now we need this other part. That the join part. So let's try to write what we need to get. We need to get a natural transformation from M composed with M to M, which is UF, and this is UF. And we have here something that helps reduce FU to identity. So we can reduce this FU, and I get a natural transformation here. It will look like this, that it takes component-wise, if you take A here, it will take, so join, it's called epsilon, epsilon f of A will be a map from fu f of A to f of A, because it maps fu to identity, and this is the component we take. And then we can take f map of it, f map of epsilon of, which this f map uses the u as the functor. Okay, so we get this composition, and the equalities that I left blank here will actually are enough to fulfill this these two axioms that we'll skip proving, the associativity and unity. Thank you. Okay, this way this way we got a monad M, which is a monad on the category of set, so it's a functor from set to set. We actually know how to write it, that if you take set S, what will be the result? What set will you get? So we take free monoid and then forget that it was a monoid. So we take the underlying set. So it will consist of these words where Si belong to S. And actually how the monad will look like, if you take words of words, which is M of M, then you can just concatenate them and consider it as a just longer word. Okay? And the same, the return is take the words of length 1, which is from S to M of S. But then there is actually interesting story going, just starting here, that you can recover the category of monoids from this monad M. And this is actually why mathematicians get really interested in monads. Is that if we started with a category of monoids, we get these two functors f and u to set, and we could take category of M algebras, which I'll define in a second. These are just maps from M of A to A with so these are the objects. We still need to define what are the morphisms. Morphisms are morphism in the category of set from A to B, such that there is a commutative diagram like that. F map F. So if we have two algebras, M algebras, and a morphism, this morphism has to satisfy some algebraic condition to be a morphism of algebras. And then again, we actually can forget that we have this algebra part. So we have a functor that forgets this from having this morphism, M of A to A. It just maps it to A. And it turns out that there is also a free functor which takes a set and maps it to and this is the join, and it looks like an algebra.
the join itself. And this gives the other part, and actually this is also at adjunction. And then it turns out that there is a comparison factor, which is an equivalence of these two categories, which nicely fits into this diagram. So every arrow here commutes. And in this setup for monoids, this is an equivalence. So this category of M algebras reconstructs the category of monoids just from the monad. So the monad actually describes all the laws that you have in a monoid. It's and categories for which have this property are called monadic. So I think it nicely fits the monadic party. So now you know where you are. Yeah, I think it's a good time to stop.